In this video, we're going to explore what we call key exchange between two computers on the internet. So if you recall, our problem is I want to send a secret number to my friend on the internet without someone in the middle intercepting what that message is. To do this, we're going to need a little bit of mathematics. And the mathematics we're going to explore is something called a one-way function. A one-way function is really easy to do in one direction, but very hard to do in another direction. So for example, a real-world example might be scrambling an egg. It is really easy to break an egg and scramble it. It is really hard to take that egg, unscramble it, and put it back in its eggshell. We want something like that in the world of computers. So I'm going to do a little bit of high school math review. Hopefully you're aware of a thing called factoring. It may be a while since you've done this, but the idea is to take a look at a number like 14 and break it up into, say, two numbers that when multiplied together become 14. Now there's a certain type of number called a prime number which cannot be factored. It cannot be broken up into two other numbers other than 1 in itself. There are no two whole numbers that can be multiplied together to get 7 other than, say, 1 and 7. So these are all the prime numbers that are between 1 and 100. So this is our first one-way function. I'm going to take two prime numbers, multiply them together, and get the result. I'm going to give you the result, and you have to try to figure out what the original two prime numbers are. So this particular example is pretty easy. If I give you 14, you could figure it out. That's 2 times 7. So let's make it a little bit harder. I'm going to give you the number 589. I'll let you even pause this video and go back and look at all the two-digit primes that were on a couple of slides ago and see if you can determine which of those two multiplied together will become 589. I'll give you a second right now. Did you figure it out? 19 times 31. Now you might think to yourself, well, this must be easy for a computer. It can just try all of the possible combinations. And you're right. But the problem is that computers do not scale up very well. If I give you this really large number and I tell you it's two 8-digit primes multiplied together, it will take you a very, very long time. But it'll still take a computer a pretty good amount of time because there's no simple trick to be able to figure this out. The computer has to try to brute force it. And if I make the number really, really, really big, then even all of the world's computers running for 100 years won't be able to figure it out. In case you're curious, those two prime numbers multiplied together will become that really big number. So this is our example of a one-way function that a computer can use. I'm actually going to introduce one more one-way function. For the next one-way function, we're going to have to do something called modulo arithmetic, or as you may know it, simply remainders. So if I take the number 1337 and divide by 10, what I end up with is 133, but I also have 7 remainder. That 7 remainder is actually the number we're really interested in. The way we write that in computer speak is 1337 mod 10 is 7. We're only interested in the remainder. So if I take the same number and do modulo 100, then we can see the result is going to be 37. In practice, we're going to be wanting to work with prime numbers again. So if I take 1337 mod 17, we're going to end up with the number 11. So the way the one-way function works is I'm going to tell you that 3 raised to some number that's less than or equal to 17 divided by 17 is going to have a remainder of 2. And you have to try to figure out what that mystery number is. And just like working with prime numbers, this is actually very difficult for a computer to do. It's really easy to do one way, but really hard to do another way. So 3 to the 14 is a fairly big number. 4,782,969. So now I'm going to divide that by 17, and then I find out the remainder is 2. So a couple things are going on here. We're going to have a base, the 3. We're going to have the modulo 17, and then we're going to raise 3 to some power, in this case 14. And again, just like with the prime numbers, we're not going to be dealing with very small numbers like 3 and 17. We might be doing something like this. 19 raised to some power mod 86061119 is going to have this other big number. So all we're going to do is transmit that final number, and it's going to be really hard to deduce what the original number that we raised 19 to the power of is. In this case, it was the number 12345. So let's see how we can actually defeat our evildoer on the internet using this technique. So what we're going to do is give out some public information. So we're going to tell the whole world, including the evildoer, that what we're going to be doing to exchange information is raising 3 to some number, let's call it x, and then dividing by 17 and getting the remainder. So both me, my destination, and the evildoer can fully know that this is the system we're going to use. Then me and the recipient both pick a random number less than 17. And we'll do it completely at random. So I choose 7 and my destination picks 15. Now, we're the only people who know these numbers. I don't know that he picked 15 and he doesn't know that I picked 7. No one will know that information. So our evildoer cannot know that information. Next, we're going to do the calculation that I mentioned before. I will raise 3 to the 7 mod 17, and that turns out to be 11. And the destination will take 3 to the 15 mod 17, and that number is 6. And now we are going to freely transmit our two special numbers, 11 and 6. Note that our two special numbers, 7 and 15, are actually still hidden. But we've now given out the public information that my number is now 11 and his number is now 6. So what can we do with that information? Well, it turns out, with a bit of a trick of arithmetic, if I take their number 6 and then raise that to the special number 7 that I picked, I will get a new number, 14. And if the destination does the exact same thing, so they take my special number, 11, raise it to their secret number, 15, and do the same process, we both end up with the exact same number. Now, the math for this is actually fairly straightforward, but we don't need to dwell into it any more than we need to. So the key here is that we both come up with this secret number 14 that the evildoer has no way of knowing. Even though the entire world can know that we did 3 to the x mod 17, my number was 11, his number was 6. No one, unless they have a supercomputer, can determine what the actual secret number of 14 is going to be except me and the destination. So now we have our secret number of 14. We can now use that to encrypt our messages, and no one in the middle can actually intercept what we're doing, even though they have all the information needed to perform the calculation. This method is known as key exchange, and we'll explore in our next video why they're called keys.